All right, so we are going over section 4.6 in this video, limits at infinity and asymptotes. Okay, so this video will probably cover just some of this section, um, but these are the learning objectives. Calculate the limit of a function as x increases or decreases without bound. So we're going to go back to limits for a bit. We'll look at limits at infinity. Recognize a horizontal asymptote on the graph of a function. Estimate the end behavior of a function as x increases or decreases without bound. Okay. And recognize an oblique asymptote on the graph of a function. We won't really spend too much time on that one, uh, maybe in the second part of this video. And then finally, also analyze a function and its derivatives to draw its graph. So that last learning objective essentially, excuse me, essentially just puts everything together from sections 4.6, 4.5, 4.3, a lot of the knowledge, even stuff that you learned in previous classes, to be able to draw a very accurate graph of a function. Okay, so let's go ahead and jump into this, and let's take a look at any important definitions and theorems that we should know for this section. All right, so I'll start by reading this first paragraph. It says, we have shown how to use the first and second derivatives of a function to describe the shape of a graph. To graph a function f defined on an unbounded domain, we also need to know the behavior of f as x goes to positive or negative infinity. In this section, we define limits at infinity and show how these limits affect the graph of a function. At the end of this section, we outline a strategy for graphing an arbitrary function f. Okay, so what we're looking at in this uh, section is limits at infinity, right? So that's the subheader here. Essentially, we want to look at, as we go really far out to the right or to the left, what is the behavior of a function? And so we're going to define a limit at infinity um, using this definition here. It says if the values of f of x become arbitrarily close to L as x becomes sufficiently large, we say that the function f has a limit at infinity and write the limit as x approaches infinity of f of x equals L. Also, we can write this for the limit as x approaches negative infinity of f of x equals, if it gets sufficiently close to L, whatever that means. Okay, so let's take a look at a function. They gave one here in our, uh, in the textbook. So if we take a look at the function f of x equals 2 plus 1 over x, then what is the limit as x approaches positive infinity of this function, 2 plus 1 over x? Well, uh, one way that we looked at limits in the past was we would plug in numbers as x approaches, a value a. In this case, a is now infinity. And so we could plug in values into this function and see what kinds of outputs we get as x grows larger and larger. And that's what they've done in this table here. Let's see. Yeah, let's see. So they have various x values that are given. And then here is the function, what the output would be. And so we can see that for an x value of 10, the y value is 2.1. Then we increase x getting closer to infinity. You can see that the value of the output is 2.01. And if we increase a lot here to 10,000, then the output is 2.0001. And you can see the behavior that as we increase, if we were to increase x even more, this number would get closer to 2. And you can get as close to 2 as you want just by increasing x more and more. And so in this case, we would say that the limit as x approaches infinity of this function is equal to 2. And so there's something that we have to realize when we take a look at these kinds of functions. We can apply the properties of limits to apply this limit to the 2 and to the 1 over x. They are, we can consider them separate functions. So here we have the limit as x approaches positive infinity of 2 plus the limit as x approaches positive infinity of 1 over x. Okay, so the limit as x approaches infinity of 2, that is just going to be 2, because as x grows to infinity, 2 just stays the same. It's a constant. So that's 2 there. Then, now the more important one here is the second limit. The limit as x approaches infinity of 1 over x. So we're going to see this, excuse me, shape a lot, or this kind of form, where the numerator is constant and the denominator is increasing. So x is in the denominator, x is increasing to infinity. And so if the denominator increases and the numerator stays constant, this whole fraction here is going to go to 0. And so our result is going to be 2 plus 0, which is 2. That's another way that we could compute the limit here. It gets very tedious to plug in a bunch of points. And so what we can do is just, kind of take a look at the behavior of each of these, the pieces of this function. And the second one goes to 0. Okay, and just to show that the function, let's say g of x equals 1 over x, this goes to 0 as x goes to infinity. Yeah, we can just view this one on its own. And I like to think of this as, getting a piece of a cookie if you're sharing with X people. So if you're sharing with one person, just yourself, let's say just yourself, this is X is the number of people that are getting some of this cookie. Then 1 over X, then you would get 1 over 1, which is just 1. You'd get the whole cookie. So that's nice. But if you share with this cookie with 10 people and you're a kind person and you split the cookie evenly, everybody's going to get 1/10 of the cookie. And so a tenth is not very much, depending on how big this cookie is. But if we decide to share with 1,000 people, then we're going to get 1/1000th of the cookie. That's a very tiny piece compared to the whole. And so we can see that as we increase the number x, as the denominator grows larger, the fraction is going to get smaller, closer to 0, right? So, yeah, I won't even be able to draw it out, but 1/1000th of the cookie is probably going to be this like tiny little slice like this. Okay, so, and you can imagine now sharing with 1,000,000 people, you would get 1/1,000,000th of the cookie. Okay, so that's a very important idea to remember. If the denominator grows very rapidly, and if the numerator is constant, then that fraction is going to go to 0 as the denominator goes to infinity. Okay, that will come up a few times in this section. Okay, so we can now define a horizontal asymptote in terms of limits. Uh, if uh, if the limit as x approaches infinity of a function is equal to some finite value L, then we would call that line y equals L y equals L is a horizontal asymptote. Okay, so if you took pre-calculus or another class where you define a horizontal asymptote, usually you just say, it's kind of like the long-term behavior of the function. Here we can use the language of limits to define that. And this is also true. It says, or if, f of x approaches L when x goes to negative infinity, that is also a horizontal asymptote. It is possible to have two different horizontal asymptotes. So either direction would create a horizontal asymptote. Okay, so let's go ahead and move on here. Um, they give a nice example here of this function f of x equals cosine of x over x plus 1. And notice here, we have that same behavior that we were just talking about, um, where we have a denominator, and we're going to look at what the behavior of this is as x goes to infinity. Well, this is the denominator is going to grow infinitely large, which is going to make the fraction smaller. And in this case, we don't have a constant in the numerator. We have cosine of x in the numerator. But cosine of x is bounded between positive 1 and negative 1. It just oscillates back and forth between those two values. And so this is a relatively small number compared to a number that is growing infinitely large. So this fraction here is going to grow to 0 as x goes to infinity. And since there's also a plus 1 there, then the limit as x approaches infinity will be 1 plus 0, which is 1. And you can see, since that limit exists, we call y equals 1 the horizontal asymptote for this function. All right. Nice. And what they talk about here in this paragraph is, that it says right here, a function may cross a horizontal asymptote an unlimited number of times. If you take a look at that, that horizontal asymptote gets crossed a whole lot, but only vertical asymptotes are the ones that cannot be crossed. A function cannot cross a vertical asymptote. But a horizontal asymptote, your function might cross it or it might not. Sometimes they don't cross it, but sometimes they do. Okay, so let's take a look at here we go. Nice, a few examples here. And so here's where we need to know graphs of functions quite well to be able to determine some of these limits. But let's take a look here. It says, for each of the following functions f, evaluate the limit as x approaches infinity of f of x. So the limit as x approaches infinity of 5 minus 2 over x squared. And so that's going to be the limit as x approaches infinity of 5, the constant, minus the limit as x approaches infinity of 2 over x squared. Okay, so here we have a limit of 5. The behavior that we talked about just a moment ago is that this denominator is going to grow infinitely large, which makes this fraction infinitely small or infinitely close to 0, effectively 0. So the limit there will be 0, and we get just 5. The same behavior will happen uh, for negative infinity as well. We can actually graph this function. This is one of the functions that we spoke about in an earlier lecture. So I forget what section it was, but it was in chapter 1, where we talked about the behavior of a function that has this form. Let's say 1 over x squared. Let's start with that one. That's going to look something like this. And so we can see that its behavior is that it trends down as x goes to positive infinity, the y value goes to 0. And as x goes to negative infinity, the y value also goes to 0 there. And so putting a 2 on top is just going to stretch this vertically. So it will change the shape a little bit, but the end behavior is still going to be the same. It stretches a little bit. You can go to desmos.com and see the difference in those two graphs. It roughly has the same shape. And then putting a negative in front of the 2x squared is just going to reflect it about the x-axis. So this is then going to become this graph here. But the limit at infinity is still going to be the same. It's still going to be approaching 0 as x goes to infinity, or as x goes to negative infinity. The function value gets close to 0. And then finally, adding this 5 shifts the whole graph up 5 units. Let me delete a couple things here. If we were to shift this graph up 5 units, 2, 3, 4, 5, then we can see that the limit is going to be at the horizontal line, y equals 5. Okay, so there's another argument for how we can get a 5 just by knowing the graph. All right, nice. Let's take a look at the next one here. Sine of x over x, f of x equals sine x over x. Remember that sine x is bounded between -1 and +1. Forgot my x. And so we have essentially something that's pretty small. Now, x, we're going to take the limit as x goes to infinity. So this is this denominator is going to grow infinitely large. That's going to make this whole fraction uh, very small, close to 0. Okay, let's take a look at how they approach this problem here. Okay, so they use the algebraic limit laws. Good. And so that's kind of what we did there. And then they actually split up 2 over x squared. They factored out the 2, and then they wrote 1 over x squared as 1 over x times 1 over x. The limit of each of these is equal to 0. And so that just gives you 0. So 5 minus 0 equals 5. All right, and there's the graph. Looks basically the same as what I graphed. All right, they're starting something similar for part B. They mentioned that sine of x is bounded between -1 and +1. So if we divide that inequality by x, ah, that's a nice argument as well. Um, they can use the squeeze theorem to say, well, let's just take the limit of all 3 of these functions. And hey, 1 over x, we know the behavior of 1 over x. As x goes to positive infinity, 1 over x goes to 0. So this is 0. What about -1 over x? Uh, g of x equals -1 over x. Well, that has the behavior that looks like this. It's just a reflection of 1 over x about the x-axis. And as x goes to infinity, y goes to 0. So this is 0 as well. Since both of these functions have a limit of 0, then the function in between those two should also have a limit of 0 as x approaches infinity. So that's the conclusion. That's a pretty nice way of doing it. The argument that I gave earlier is also fine. This is bounded between -1 and +1. The denominator grows infinitely large, making the fraction close to 0. Okay, nice. You can do the exact same thing as x goes to negative infinity. Um, we can make the same argument. Okay, so where is the graph? Here's the graph. Kind of bounces back and forth a little bit, but it quickly approaches 0. Uh, it's yeah, going to 0 on both the left and the right side. And it will just continue to oscillate forever. Um, but it gets arbitrarily close to 0. Okay, the last one, this tangent inverse, there's basically no way around it. You need to know what the graph of the tangent inverse function looks like. And so just a quick reminder from pre-calculus or wherever you graphed the tangent function. Tangent of x looks like this, from -pi/2 to +pi/2. And there are, vertical asymptotes there. And so when we invert this, we get a graph that looks like this, where now our vertical asymptotes have become horizontal asymptotes. And the limit as x approaches infinity is going to be, we can see from the picture, is equal to pi over 2, and the limit as x approaches negative infinity of this function is equal to negative pi over 2. So knowing the graph is crucial for this problem here. Let's see, they show the tangent of x, which is right there. And then, yeah, they show that the limit as x approaches pi over 2, let me see here. Yeah, pi over 2 from the left side. So as we approach pi over 2 from the left side, what happens to the function? It goes to positive infinity. So then for the inverse function, the limit as x approaches positive infinity of the inverse function, tangent inverse x, is equal to pi over 2. Okay, so yeah, I think it's clear if you just draw out the tangent inverse function graph, and then you can just see it from the picture. All right, very good. So y equals pi over 2 and y equals negative pi over 2 are horizontal asymptotes of this tangent inverse function. And we can see that clearly that a function has multiple and different horizontal asymptotes. Okay. Oh, there it is. Nice. There's a couple of problems here that you can try on your own. We will continue. So what if the behavior at infinity is that your function doesn't actually approach a single value, like pi over 2? We could have infinite limits at infinity. And so sometimes you increase x without bound. So x is increasing here from 10 to 1000. And you see that f of x, the function, ends up just increasing a whole lot too. In this case, we would say that the limit is just positive infinity, that the function just continues to grow without bound. Um, Or if you take x to approach negative infinity, you make the x value very negative, then the function may approach something that's infinitely large in the negative direction. So we would say it approaches negative infinity in that case. Okay, so let's see, there should be some definitions here. Here we go. We say that a function f has an infinite limit at infinity and write the limit as x approaches infinity of f of x equals infinity if f of x becomes arbitrarily large for x sufficiently large. Basically, it's just saying if you go very far to the right and your function goes very far up, it just becomes very large, um, well then we would say that that function has an infinite limit at infinity. A lot of functions are like this. The line y equals x, y equals mx plus b, where m is positive, also has that behavior. As you go very far to the right, the function goes very high up, without bound. It'll just continue to go up the further you go to the right. Okay, and there's some formal definitions. We're not going to talk about these formal definitions, but if you want to know more about them, you can visit me during my office hours. Yeah, we generally skip that. Okay, so let's take a look. Um, ah, no, this is using the formal limit. We'll skip that. Okay. So end behavior is our next topic. This is a topic that has probably been covered in a pre-calculus class or an algebra class that you took in the past, but we'll review it a little bit. So let's see what it says. It says the behavior of a function as x goes to positive or negative infinity is called the function's end behavior. At each of the function's ends, the function could exhibit one of the following types of behavior. Yeah, so at the end, it can approach a horizontal asymptote, y equals L. It can go to positive or negative infinity. Or number three, it says the function does not approach a finite limit, nor does it approach positive or negative infinity. In this case, the function may have some oscillatory behavior. And so that's like a function like the sine function. It never approaches a single value, but it also doesn't go to infinity. It just kind of continues to go up and down. Okay, so let's take a look at different types of functions and their end behaviors. So the one that you've probably seen before is for polynomials. So for polynomial functions, if you have, let's say we look at the function f of x equals x to the n, where n is even, where n is even, that's the graph that they're showing here, um, then you get functions like y equals x squared. And the end behavior is that both ends go to positive infinity. Um, so the limit as x approaches positive infinity of this function, let's say x squared, for example, is going to be positive infinity. The limit as x approaches negative infinity of x squared is also positive infinity. Both ends go up, and this can be changed if you, of course, if you were to reflect this about the x-axis, if you were to multiply by a -1, but then in that case, there you would have a negative x squared. That negative could be factored out. And so you would still do the limit of x squared, which is infinity, and then just multiply that by -1. Um, and that would give you negative infinity. Okay, so we need to know the rough idea here is that if the exponent of this power function is even, then assuming the leading coefficient is positive, both ends point up. So both limits at infinity are positive infinity. Now, this is different when n is an odd number. Let's take a look at if n is odd. Here we can look at the function, uh, let's say y equals x cubed. What does that look like? It looks like this. The function y equals x also has the same type of end behavior. And the end behavior that we're talking about is that this function, let me call it g of x equals x to the n, where n is odd, is that the limit as x approaches positive infinity. So here we do need to pay close attention. Oops, and that's called g of x. We do need to pay close attention as to if we're approaching positive infinity or negative infinity. If we're approaching positive infinity, then the function g of x tends to positive infinity. And if we're uh, going to the left to negative infinity, then we can see that both of these functions where n is odd are going to negative infinity. Okay, so that's the difference in the power function between odd and even exponents. Okay, and then they talk about, they talk a little bit about here what if the leading coefficient c is positive? Well, that's not going to change anything on these limits, but if c was negative, then it's going to flip all of these limits and it will change their signs because of the reflection about the x-axis. Okay, so let's go ahead and take a look at some, here we go. Let's take a look at some examples. So example A, we want to find the limit as x approaches positive infinity for this -5x cubed. And so the quickest way to do this is just to graph the function or sketch a graph of -5x cubed. That's like the x cubed function, but with the -5 that reflects it about the x-axis. So it's going to look something like this. And so we can immediately see that the limit as x approaches positive infinity is going to be negative infinity. That is negative infinity. Now, if you wanted to do this a different way and maybe factor out this -5, let me do the limit as x approaches negative infinity of -5x cubed. So let's suppose I don't know what negative 5x cubed looks like, but I know what x cubed looks like. I can factor out this negative 5, multiply by the limit as x approaches negative infinity of x cubed. And then I go back to my x cubed example that I did over here. And I said, hey, as x approaches negative infinity, this function goes to negative infinity. So this would be negative 5 times this limit, which is negative infinity. And these things multiply. The negatives will cancel. You get 5 times positive infinity, which is just an infinitely large number. So the limit on this side is positive infinity. We can leave off the positive, but I'll just write it there to stress that it's positive. Okay, nice. So then the last one here for b, 2x to the fourth is going to look something like this. It's an even exponent, and there's a positive leading coefficient, so both ends point up. That means that both limits at infinity are going to be positive infinity. Now all we have to do is write it out. The limit as x approaches positive infinity of 2x to the fourth, and the limit as x approaches negative infinity of 2x to the fourth is equal to positive infinity and positive infinity for both. Well, that was easy. If we know what the graphs look like, we can, pretty easily uh, evaluate these limits. Now let's just read what they said here. Since the coefficient of x to the fourth is positive 2, the graph of f of x equals 2x to the fourth is a vertical stretch of the graph of y equals x to the fourth. Therefore, the limit is positive infinity on the left side and the right side. Okay, yeah, they didn't really give too much insight on that. But yeah, we're just using this idea over here. Here's x to the fourth right there. The limit as x approaches negative infinity or positive infinity is positive infinity. You just put a 2 in front of that. It just stretches it, but it still goes to positive infinity on both sides. Okay, so all of those function transformations that we learned about in the past are very important. So, um, okay, so that was a basic power function, just like x to the n or 2x to the n. What if we have a more general polynomial? F of x equals a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, and so on. What this shows here is that we could actually multiply this polynomial by 1 over, or what do they do? They do something a little bit differently here. Yeah, they factor out an ax, a sub n, x to the n from this. If we factor that out from the first term, we get 1 plus, uh, yeah, a sub n minus 1 over a sub n times 1 over x. And we could factor out this term here, this leading term. And what this would show us is actually that most of these terms are not going to matter when we take a limit as x approaches infinity. Because as x approaches infinity, notice this factor here, this factor of 1 over x is going to go to 0. The other terms are also going to have a similar 1 over x to some exponent, which are also going to go to 0. 1 over x to the n goes to 0. And so, in a sense, the only term that really matters is this leading term for a polynomial. The leading term determines the end behavior. This is probably something that you learned in pre-calculus, and so we're just kind of stating that again. So the limit of the function f of x, where f of x is a polynomial, really is just equal to the limit as x approaches positive or negative infinity of that leading term, a sub n x to the n. So the simplified version here is just look at the leading term, take the limit of that term, and that's the limit of the polynomial. For example, here's a polynomial with 3 terms, and notice they just look at the leading term, 5x cubed, and they have the same behavior, right? They are different functions, as you can see in this graph. They're different functions. They're clearly different colors, different shapes, but the end behaviors are the same. The end behavior of a polynomial is determined by the leading term. All right. A polynomial's end behavior is determined by the term with the largest exponent. Okay, nice. Very good. All right, now we're going to speed this up a little bit here. I think this is going on a little long. Let's see, how do I see how long? Hmm. Ah, okay. So let's go ahead and continue. So how do we determine the end behavior for a rational function? Um, that's our next little topic here. There's a lot of different type of functions that we know about. So um, we'll start with rational functions. That's the next type of function that we study. And so it says here for parts A, B, and C, for each of the following functions, determine the limits as x approaches infinity and negative infinity. Then use this information to describe the end behavior of the function. Okay. Um, now I think they give us a little rule here to use. It says here to evaluate the limits at infinity for a rational function, we divide the numerator and denominator by the highest power of x appearing in the denominator. This is going to be useful for us. So let's do that. So in the denominator, we have the highest power appearing in the denominator is x to the first power. And so in order to do the limit of this function, excuse me, function f of x as x approaches infinity, we're going to divide. Let's start with we'll start with positive infinity of 3x minus 1 over 2x plus 5. And notice we're going to divide both the top and bottom by x. That's the same thing as multiplying by 1 over x on the top and bottom. And so let's go ahead and do that. And we'll see the usefulness of this in just a second. The limit as x approaches infinity of 3x, already, yeah, 3x over x minus 1 over x. So I'm just distributing this 1 over x to both of these terms, divided by 2x over x plus 5 over x. And then let's simplify a bit. This is the limit as x approaches infinity of 3 minus 1 over x over 2 plus 5 over x. And so the reason that this is so useful using the degree of the denominator is that we can see that this 5 over x term is going to go to 0 as x goes to infinity. The 1 over x term is also going to go to 0. And then by using the degree in the denominator, that is essentially going to guarantee that one of these terms is just a constant. And so when we divide by x, this term is going to be 2, which its limit is going to be 2 in the denominator. And so our limit ends up being 3 minus 0 over 2 plus 0, which is just 3 over 2. And that's very nice. Quite, quite simple. You may have learned a rule in pre-calculus that said if the degree on the top and the degree on the bottom are the same, then the horizontal asymptote is just, you just divide these leading coefficients. And this method that we're using here is the way that you come up with that rule. Okay, nice. Um, okay, if we were to look at the limit as x approaches negative infinity, so let's put a negative there. Essentially, this would still be the same. Let's see here. Would there be any change? Well, we would do the limit as x approaches negative infinity of 1 over x. That still goes to negative infinity. This also goes to, sorry, each of these still go to 0 um, because 1 over x looks like this. So as x goes to positive infinity, this function 1 over x goes to 0. As x goes to negative infinity, the function still goes to 0. So those are still zeros. The horizontal asymptote is going to be 3 halves both times. So here we'll write it just to be complete here. The limit as x approaches negative infinity of this function 3x minus 1 over 2x plus 5 is equal to 3 halves. All right, the work would be the same. Okay, so what about if the degree of the numerator is less than the degree of the denominator? Let's take a quick look at that. Yeah, let's look at that. So here for part B, we'll look at the limit as x approaches, let's do positive infinity of 3x squared plus 2x over 4x cubed minus 5x plus 7. And we multiply by the biggest degree in the denominator, which is x cubed. So we divide by that. So multiply by 1 over x cubed. And so I'm going to multiply and simplify all in one step because this is a long section. The limit as x approaches positive infinity of this 1 over x cubed is going to be 3 over x plus 2 over x squared divided by 4 minus 5 over x squared plus 7 over x cubed. When we do the limit as x approaches infinity, denominator grows, the x cubed grows to infinity, making that fraction 0. X squared grows to infinity, its numerator stays constant, so that fraction goes to 0. This goes to 0, this goes to 0, and so this is just 0 over 4, which is 0. Okay, very nice. Yeah, and yeah, they show all of this work here in the book, so feel free to walk through it. They're very efficient here, and they actually even just say it's going to be the same for positive or negative infinity, so they just put a plus or minus infinity there. I would recommend doing them separately until you kind of master this topic. And then they show the graph. You can see the behavior there. For part B, we only did the limit as x approaches positive infinity, but the negative infinity is going to be done in a very similar way. Again, they do it all at once in this. They divide the numerator and denominator by x cubed. That's what we did. So there is the behavior as x goes to positive or negative infinity. Now let's take a look at part C here, because these are going to be different. Yeah, let's see here. The limit. We are not going to get too far into oblique asymptotes, but we can look at the limit. The limit as, let's see, x approaches infinity of 3x squared plus 4x over x plus 2. So what were we told by that line in the textbook? It said multiply or divide by the term that has the biggest exponent. So 1 over x to the first power. The denominator is of degree 1, so we divide by a degree 1 term. Okay, so this becomes the limit as x approaches infinity of 3, let's say 3x squared divided by x is just 3x plus 4 divided by, here we get 1 plus 2 over x. And so here we do need to pay closer attention because one of these terms will go to 0. So we're going to have 0 plus 1 in the denominator. But in the numerator, uh, we're not going to get a constant, nor is it going to go, all to 0. And so we have to pay close attention to what 3x plus 4 does as x goes to infinity. And so we know the graph of 3x plus 4, that's y equals mx plus b. So that looks something like this. The limit as x approaches positive infinity is positive infinity. So here, this limit is going to be positive infinity. And then the other direction we should look at as well, the limit as x approaches negative infinity of this function, 3x squared plus 4x over x plus 2. We'll scale it here. We've already done the work, so we'll just write it down again. The limit as x approaches negative infinity of, this is going to come out to 3x plus 4 over 1 plus 2 over x. As x goes to negative infinity, this 2 over x term is still going to go to 0. The 1 is still going to have a limit of 1, so we have 1 in the denominator. But now we need to ask, what does 3x plus 4 approach as x goes to negative infinity? Well, we can see that from the graph. As x goes to negative infinity, the function approaches negative infinity. And so this is going to have a different answer, not positive infinity, but negative infinity. And now we see the graph right there of the actual function f of x, and we can see that as x goes to positive infinity, the function does seem to be approaching positive infinity, and as x goes to negative infinity, the function is approaching negative infinity. All right, very good. There's a lot of material in this section, so um, this will be a little bit longer than most videos. Um, all right, so then they talk a little bit about oblique asymptotes. I'm not really going to cover that. Um, you can read that yourself. It's nice. Um, yeah, let's go ahead and we'll skip that. So we have quite a bit here still left. So we can, yeah, let's go ahead and take a look at one more. Yeah, just so we kind of wrap this up a bit. And this last example, example 4.2.6, is it's going to be similar to what we did in the previous problem, but if the function has a radical in it, then we need to figure out, so what's the method for determining a limit as x approaches infinity for this kind of function? Well, something that we need to know for this function here, let's see here, how can I do this? Um, Something that we need to know is the graph of f of x equals the square root of x squared. This is equal to the absolute value of x, which is equal to uh, the piecewise function x if x is larger than or equal to 0, or negative x if x is less than 0. Okay, so let's just quickly graph this. The absolute value function, I'm sure you're all very familiar with it. Um, it looks like this, like a V. And so we can see how that would be just y equals x if x is larger than or equal to 0. Let me graph that in blue. Y equals x. The line y equals x looks like this. It's just this line with slope 1, but we only want a piece of this line. When x is larger than or equal to 0, gives us exactly that portion of the absolute value function. And then y equals negative x. This is a downward sloping line. And if we restrict this to where x is less than 0, then here is the whole line, right? But if we restrict it to where x is less than 0, that's going to give us just this portion. And notice how those make up the absolute value function. Okay, so that's going to be useful here because we are going to look at the limit as x approaches positive infinity of 3x minus 2 over the square root of 4x squared plus 5. And so the method that they uh, recommend in this book here is to multiply the top and bottom, just like we did before. We divided by the degree of the denominator. Here in the denominator, we have 1 over, there's an x squared, but it's inside of a square root. So we can multiply by 1 over the square root of x squared on both the top and bottom. But then knowing that the square root of x squared is equal to the absolute value of x, and that this is equal to uh, just x when you're dealing with x's that are larger than or equal to 0, which is what we're dealing with here because we're looking at x as x goes to positive infinity. Essentially, we can reduce the square root of x just to the square root of x squared just to x. So this becomes the limit as x approaches infinity of 3x minus 2 over the square root of 4x squared plus 5. In the numerator, since I only have x's and I don't have a square root, I'm going to write the square root of x squared as just x. In the denominator, since I do have a square root, I'm going to leave that as the square root of x squared, and that way I can multiply this square root of x squared into the other square root. And so that's going to give me the limit as x approaches infinity of, let's see, 3x times 1 over x is 3, minus 2 over x. That's the numerator. In the denominator, I'm going to get the square root of 4x squared divided by x squared is just 4. And then 5 divided by x squared is plus 5 over x squared. And so we can see that as x goes to positive infinity, this goes to 0, this goes to 0. And so we're going to get as our answer 3 over the square root of 4, or 3 over 2. Okay. So notice that's what we end up getting for our answer. They did the exact same thing here. Yeah, they multiply by 1 over the absolute value of x. Sure. That ends up reducing to 1 over x that they use in the numerator. And then for the denominator, the 1 over absolute value of x, they end up using a 1 over x squared in the square root. So 1 over the square root of x squared. All right, so this can be a little bit complicated. Let's go ahead and do the other side. I do believe, yeah, the other side comes out to a different value. And it has something to do with the fact that the absolute value function is defined as a piecewise function. So let's go ahead and take a look at that very quickly. The limit as x approaches negative infinity. So the negative infinity is very important here, of 3x minus 2 over the square root of 4x squared plus 5. So as we said, we want to multiply by 1 over the square root of x squared in the denominator. We'll multiply by the same thing in the numerator, but yeah, let's go ahead and leave it as 1 over the square root of x squared. Okay, since there is no square root in the numerator, we're going to rewrite that for the numerator. And for the denominator, we'll leave it the same. So 3x minus 2. Well, how can we write 1 over the square root of x squared? Well, we said earlier that the square root of x squared is equal to the absolute value of x. But in this case, since we're dealing with negative numbers, numbers less than 0, the absolute value of x is going to take on the form negative x, or the opposite of x. And so this is going to be negative 1 over x. In the bottom. In the bottom here, we can just distribute. Since both of these have a square root, we can just distribute that 1 over x squared right into. You can think of this as the square root of 1 over x squared, if you like. And so we multiply. Since they're both under the square root, we can just multiply that 1 over x squared into the 4x squared plus 5. And that would give us a 4 plus 5 over x squared. All of that is inside of the square root. So we got to know what properties of exponents or properties of square roots for this. And so notice there's the big difference, that negative coming from that absolute value function. Since we're dealing with x values that are getting closer to negative infinity, they're all negative, then the absolute value of x in that case is not just x, but negative x. So there's an extra negative here that we have to uh, keep in mind. So the limit as, let's go ahead and as x goes to negative infinity, we distribute this negative 1 over x. That's going to give us a negative 3 plus 2 over x over the square root of 4 plus 5 over x squared. As x goes to negative infinity, this goes to 0, this goes to 0, and so we end up with a negative 3 over the square root of 4, or negative 3 over 2. Nice. That's a little bit complicated. It's not, I would not say that that's super simple. So definitely, it takes some practice to do this. And that's the reason that I'm making this video. There's the graph. Oh, no, look at that. One of those horizontal asymptotes gets crossed. Here's a problem that you can try yourself, 4.25. Um, yeah, and then I'll only just comment on this last problem here, and then we'll stop there because so just very quickly, it talks about the textbook talks about there are some functions that don't have a limit as x goes to infinity, as we mentioned earlier, like the sine function. We would just say the limit does not exist there. The tangent function also doesn't have a limit. It looks like it's going to infinity, but then it drops down and it kind of just keeps repeating. So as x goes to positive infinity, as we go very far to the right, the function isn't just continuously going up, it drops down at points and then goes up, and then drops down again and goes up. So we would say that the limit does not exist for the tangent function as well, as x goes to infinity or negative infinity. The exponential function, y equals b to the x, that looks like this. This is one that we need to know really well. So the limit as x approaches infinity of b to the x, like 2 to the x, e to the x, 5 to the x, that's going to be positive infinity. We can tell from the graph. What's the limit as x approaches negative infinity of this exponential function, b to the x? Well, we can see right here from the graph, as we go to negative infinity, the function is falling down towards 0. And so this limit is equal to 0. We need to know those, those parent functions and their limits as well. And then finally, the logarithmic functions, let's say log base b of x, f of x equals, the natural log function is a very common one, but this can be extended to the log base b of x. They all kind of have the same behavior. Let me not put it equals there. They're not the same function, but they have the same behavior in the parent function. And so the limit as x approaches positive infinity, as we go to positive infinity, this function does continue to rise to infinity. So for let's say for the log base b of x, this is positive infinity. And the limit in the other direction, can you guess what the limit as x approaches? Actually, the limit as x approaches negative infinity would not exist. So I'm not going to, because this function does not go to negative infinity because it's not defined for x values less than 0. So we could also say that the limit, let's take a look at the limit as x approaches 0 from the right of the natural log of x, or log base b of x. This is negative infinity. We can see that behavior. As we get closer to 0, the function goes to negative infinity. All right, so there we have it. And this is exactly what they say right here. There and there. Okay, you can see that from the graph. So just very quickly to comment on this last problem, how would we do this? How would we do the limit as x approaches, let's say, positive infinity, of 2 plus 3 e to the x over 7 minus 5 e to the x. If we were just to analyze what the functions do, 2 plus 3 e to the x looks something like this. That top function goes to infinity. 7 minus 5 e to the x looks something like this. It's reflected about the x-axis, scaled by a factor of 5, and shifted up 7 units. And so that limit is negative infinity. Excuse me. As x goes to the right, y goes down to negative infinity. So positive infinity divided by negative infinity, that's not something that we can, determine right now. So we need to kind of manipulate this algebraically. And so what we can do is, similar to what we did with polynomials, we can multiply by 1 over, the degree, or the biggest exponent. It's kind of the same idea that we're going to use here, but this is a constant function, 7, and this is a function that is increasing e to the x very quickly. So we can multiply by 1 over e to the x to kind of rescale both the numerator and denominator. And let's see what's going to happen here. We had a function that was constant, 2, and then one that was going to infinity. But if we multiply by 1 over e to the x, the limit as x approaches positive infinity of, so let me distribute this now. This is going to be 2 over e to the x plus 3. The e to the x's would cancel over there in that second product. And then in the denominator, we have 7 over e to the x minus 5. And so now we have e to the x's in the denominator. These e to the x's will grow to positive infinity as x goes to infinity. And so what happens when a denominator grows infinitely large and a numerator stays constant? We talked about that before. That fraction is going to go to 0. This is also going to go to 0, and that is going to leave us with a 3 over 5 as our answer. Okay. So let's take a look here at what they say. To find the limit as x goes to infinity, we divide the numerator and denominator by e to the x. Okay. They do that, and they get exactly the same thing that we did just a moment ago. And then if e to the x goes to infinity, then the denominator is going to infinity, which makes the whole fraction go to 0. And that's true for both terms that have e to the x in the denominator. And so then you get 0 plus 3 divided by 0 minus 5. And they're getting a negative 3/5. Yes, oops, I made a mistake there. There was a negative. Here, I'll put it in purple. And so my answer should have a negative 3/5. Now, okay, that's nice. That was not too different from what we did before. So let's look at the limit. This is the last thing we'll do here before we end. The limit as x approaches negative infinity of 2 plus 3 e to the x over 7 minus 5 e to the x. In this case, we don't have to do the rescaling that we did earlier, because as x approaches negative infinity, what does e to the x approach? We just talked about it over here. E to the x, as x approaches negative infinity, e to the x approaches 0. And so just automatically by taking the limit, yeah, actually, let me split this up. This is the limit as x approaches negative infinity of 2 plus the limit as x approaches negative infinity of 3 e to the x divided by the limit as x approaches negative infinity of 7 minus the limit as x approaches negative infinity of 5 e to the x. Well, yeah, We didn't really have to write all of this out, but I wanted to, do it in pieces. Uh, as x approaches negative infinity, e to the x goes towards 0. So 3e to the x goes towards 0 as well. That limit is 0. This limit here is 0. And so now we just have limits of constants. The limit as x approaches negative infinity of 2 is just going to be 2. So we get 2 plus 0 on top, 7 minus 0 on the bottom. And so that is 2 over 7. That is our horizontal asymptote. So this function has two horizontal asymptotes. And that's the end of that problem. Nice. This is a very good one to try just to kind of practice yourself. See if you can do that. And then you can use something like desmos.com to graph the function and see if your horizontal asymptotes are in fact what you computed them to be. All right. Um, I don't have time to go over the rest of this section at this point. But it is a good idea to read through it and kind of know how to put everything together to be able to sketch a really good graph of a function. I may do this in a future video, so subscribe to see when more videos come out. But that will be for another time. All right, I hope you enjoyed the video. Sorry for making it so long. Um, But make sure to leave a like on the video or leave a comment. And if you like watching the videos, leave a comment and let me know so I can continue to produce them.